Reality looks solid and predictable. A ball rolls when pushed. The sun rises each morning. Apples fall from trees. These patterns follow the laws of classical physics, discovered by Isaac Newton and refined by Albert Einstein. But when scientists looked deeper into the world of atoms and particles, they found a universe that defies common sense. At this smallest scale, particles behave like waves. They can exist in two places at once. They can tunnel through barriers. Their behavior is not certain, only probable. This strange and powerful science is called quantum mechanics. It is the foundation of modern technology, from semiconductors to lasers to quantum computers. It also challenges our deepest ideas about reality. In this documentary, we will explore the mysteries of quantum mechanics, explain its key principles in simple terms, and reveal how it shapes the universe and our future. At the dawn of the 20th century, physics was at a crossroads. Classical theories could not explain new experiments. One puzzle was blackbody radiation, the way objects glow when heated. Classical physics predicted an infinite amount of energy at short wavelengths, known as the ultraviolet catastrophe. But experiments did not match. In 1900, Max Planck proposed a bold solution. He suggested that energy comes in tiny packets, which he called quanta. This was the birth of quantum theory. Soon after, Albert Einstein explained the photoelectric effect, showing that light itself behaves as particles, which we now call photons. This discovery earned him the Nobel Prize. Over the following decades, pioneers like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger built a new framework for understanding matter and energy. They discovered that electrons orbit atoms in discrete levels, that particles can exist in multiple states at once, and that measurement itself influences reality. This revolution reshaped physics. It explained the structure of atoms, the behavior of materials, and the processes inside stars. It also opened the door to technologies that power the modern world. Quantum mechanics began as a theory of the very small, but today, it stands as one of the most successful scientific theories ever created. One of the strangest lessons of quantum mechanics is that particles are not simply particles. They can also behave like waves. This idea was confirmed in the famous double-slit experiment. When light passes through two narrow slits, it creates an interference pattern on a screen, like ripples on water. That is expected if light is a wave. But when scientists sent particles of matter, like electrons, through the slits one at a time, the same interference pattern appeared. Each electron acted as if it were both a particle and a wave, interfering with itself. When detectors were placed to observe which slit the electron passed through, the interference vanished. The act of measurement changed the outcome. This wave-particle duality applies to all matter. Tiny particles like protons, neutrons, and even larger molecules can display wave behavior under the right conditions. It means that the universe at its core is not made of solid billiard ball particles. It is made of entities that can act as both waves and particles, depending on how we look. This discovery is not just strange. It is a foundation of modern physics. It explains how atoms hold together, how electrons orbit nuclei, and how light interacts with matter. Wave-particle duality shows us that reality is not fixed. It is flexible, shifting between possibilities based on how we observe it. If wave-particle duality is strange, the uncertainty principle is even more unsettling. In 1927, Werner Heisenberg discovered that certain properties of particles cannot be known with absolute precision at the same time. For example, the more precisely we know a particle's position, the less precisely we can know its momentum. This is not a flaw in our instruments. It is a fundamental property of nature. At the quantum level, particles do not have exact values until they are measured. The uncertainty principle has profound consequences. It means that reality is not deterministic. We cannot predict the exact future of a particle, only the probability of different outcomes. This uncertainty is not just a limitation. It is what allows atoms to exist. If electrons had exact positions, they would collapse into nuclei. Instead, their uncertain positions create stable orbitals that form the basis of chemistry and life. The uncertainty principle also allows phenomena like quantum tunneling, where particles pass through barriers they should not be able to cross. This effect powers the nuclear fusion in stars and the operation of modern electronics. Heisenberg's principle shows us that uncertainty is not ignorance. It is woven into the fabric of the universe. The world at the smallest scale is not rigid and predictable, but fluid and probabilistic. One of the most fascinating ideas in quantum mechanics is superposition. It means that a particle can exist in multiple states at the same time until it is measured. The most famous illustration is Schrödinger's cat. Imagine a cat in a box with a device that has a 50% chance of releasing poison. According to quantum mechanics, until the box is opened, the cat is both alive and dead, existing in a superposition of states. This is not just a thought experiment. In the laboratory, electrons, photons, and even small molecules have been shown to exist in superpositions. They can spin clockwise and counterclockwise at the same time. They can pass through two paths simultaneously. Superposition is what makes quantum computers possible. Instead of bits that are either 0 or 1, quantum bits, or qubits, can be both at once. This allows quantum computers to process vast amounts of information in parallel, solving problems far beyond the reach of classical machines. Superposition is not science fiction. It is a tested fact. But it challenges our intuition. It tells us that reality is not definite until observed. It exists as a cloud of possibilities, collapsing into one outcome when measured. Another quantum mystery is entanglement. When two particles interact, they can become linked in such a way that their states remain connected, no matter how far apart they are. Albert Einstein called this spooky action at a distance, because it seemed impossible that information could travel faster than light. Yet countless experiments have confirmed it. When two entangled particles are measured, the outcome of one instantly determines the outcome of the other, even if they are separated by kilometers or more. Entanglement is not just a curiosity, it is a resource for new technology. It underlies quantum cryptography, which promises unbreakable codes, and quantum networks, which could lead to a new kind of internet. The fact that entanglement is real forces us to rethink the nature of reality. Are particles truly separate objects, or are they parts of a deeper, connected whole? Entanglement shows us that the universe is not made of isolated pieces. It is woven together in ways that defy classical understanding. Quantum mechanics allows particles to do what seems impossible. One of the most surprising effects is quantum tunneling. In the classical world, if a ball rolls toward a hill that is too high, it stops. But in the quantum world, particles sometimes pass through barriers, even when they do not have enough energy to climb over. This happens because particles are also waves. A wave does not stop abruptly at a barrier. It fades gradually, and in some cases, part of it continues on the other side. For particles, this means there is a probability they will appear beyond the barrier. Quantum tunneling is not rare. It happens constantly. It is the reason nuclear fusion occurs in the sun, where protons can tunnel through their mutual repulsion to fuse together, releasing energy. Tunnel diodes, scanning tunneling microscopes, and flash memory devices rely on tunneling. Without it, the electronics that drive our world would not exist. Lasers, used in medicine, communication, and manufacturing, are based on quantum principles of stimulated emission. Magnetic resonance imaging, or MRI, which lets doctors see inside the human body, works because of quantum properties of atomic nuclei. Even the Global Positioning System, or GPS, relies on quantum physics. Its satellites use atomic clocks, which keep time using quantum transitions in atoms. Without quantum mechanics, GPS would be inaccurate within minutes. Looking to the future, quantum mechanics is driving innovation in quantum computing, quantum communication, and quantum sensing. These technologies promise breakthroughs in medicine, cybersecurity, materials science, and artificial intelligence. Quantum mechanics is often described as strange and counterintuitive, but it is also practical. It is embedded in the technology of daily life, shaping the present and the future. It tells us that certainty is replaced by probability, that observation influences outcomes, and that the universe is connected in ways we are only beginning to grasp. For scientists, it is a tool for making precise predictions about the smallest scales of nature. For philosophers, it raises questions about free will, determinism, and the nature of existence. For engineers, it is the foundation of modern and future technology. Quantum mechanics also reminds us of humility. The world we experience is only one layer of reality. Beneath it lies a realm that does not obey our common sense, but instead follows rules that challenge our imagination. Yet out of this strangeness comes order. Out of uncertainty comes stability. Out of quantum possibilities comes the universe itself. Quantum mechanics is a triumph of human curiosity and scientific discovery. It shows us that even when reality seems impossible to understand, we can still reveal its secrets through observation, mathematics, and imagination. At the smallest scale, the universe is not solid and predictable. It is a dance of waves and particles, probabilities and possibilities. It is a world where matter tunnels through barriers, where particles exist in many states at once, and where distant objects remain mysteriously connected. This is the hidden universe of quantum mechanics. It powers our technology, explains our origins, and shapes our future. The next time you look at a smartphone, a laser pointer, or a medical scanner, remember, all of them work because of the strange rules of the quantum world. As we continue to explore this frontier, new discoveries will emerge, technologies we cannot yet imagine, and insights that may redefine reality itself. This is quantum mechanics made simple, the science of how reality works at the smallest scale. If you enjoyed this journey into the quantum world, make sure to subscribe for more explorations of the universe.